Hi everyone, we're Team Houston, we have a solution. I'm Sims Petway.
I'm Jake Tarts.
And I'm Carson Messer.
What we're going to do today is I'm going to give you an overview of our engineering design process. Jake's going to talk about how our machine actually works, and Carson's going to talk about how this version is actually updated from a version 1 of our machine. So at the beginning of the design process for our machine, we learned how to use multiple engineering design tools to come up with a systematic process on how to solve this big problem that was presented to us. And through using tools like house quality, specification sheets, stuff like that, basically the conclusion we came to from our analysis was that we wanted to focus on complexity and actually minimizing it. It might seem intuitive that the more complex your design, the more capable it will be. But what we found, especially within the context of 2110, was that the more simple your device, the more reliable it will be, and the more robust it will be, and the more likely it can be better in the competition. And so the way we did that was we tried to combine multiple subsystems into one subsystem that could accomplish multiple tasks. And by doing that, we're eliminating potential points of failure in our system.
So how our system works is first, a linear actuator punches out this arm, which is pulled by rubber bands. It comes out and removes the first rock by hitting it. Afterwards, our linear actuator, our key simplistic mechanism, punches out the drawer slides from a gate, allowing them to fully extend. And as they do this, a pin on top is pulled, releasing these flappers to hit the next two rocks. Following that, a solenoid that's positioned on a variable timer depending on where our zone is relative in front of us is pushed in, releasing a flap that allows the balls to roll out and into the zone. Following is a motor that rotates the arm up, plants a flag on top of the lunar landing zone, and then returns. Lastly, the actuator retracts, pulling back the whole system, allowing for complete regression.
This final design that Jake just explained is very similar to version 1, but with a few key updates. We have the same base and frame from version 1 in here, but we made it much more reliable. Initially, we had a solenoid and string system to where when the solenoid initiated, it extended the system, but the system only relied on gravity to extend, so therefore it didn't always fully extend. We also had stanchions and casters up here, which pushed the rocks out of the way, but they also sometimes got stuck. So now we have the slapper that pushes the rocks back into open space. We also had a string and pulley system up here for the flag, which extended the flag up onto the lunar ridge and brought it back. And we had another string and pulley system back here, which winched the system back for aggression. However, the string was very unreliable and would break when the motor would turn.
So that version 1 that I just talked about did not fare well in competition. In the preliminary competition in our section, we placed dead last.
So what we did with that was we took the feedback from our machine's performance there and used it to iteratively update our design by removing poorly functioning subsystems and replacing them with much more reliable and more robust subsystems. And what that allowed us to do was actually do very well in the qualifying competition, and we got a 7th seed out of 48 teams.
So overall, we're really excited for the final competition and would like to ask Houston, do we have a problem? No, Houston.
We have a solution.